Hello, my name is Andrew Berquist, and today our goal is to prove using weak induction that 9 to the nth power minus 1 is divisible by 8 for all possible integer values of n, such that n is greater than 0. I've written that out for us here, and we're going to start this problem in the belief phase. We're going to first convince ourselves that it makes sense before we formally prove it. So let's start with n is equal to 1. We can consider n equal to 1 the base case for our problem because it is the lowest integer value of n that is greater than 0. So, does 9 to the first power minus 1 equal 8 times some multiple for the purpose of this problem, which we're going to call y? Well, yes it does. As you can see here, 9 minus 1 is equal to 8, which is quite clearly equal to 8 times 1. Great. So, does this process work for n equal to 2? Well, let's try it. 9 squared is equal to 81, and 81 minus 1 is equal to 80. Well, 80 can be rewritten as 8 times 10, where our multiple y is equal to 10, and once again, we've shown that 9 to the nth power minus 1 is divisible by 8. Okay, let's try this one last time. Let's take 9 to the third minus 1. 9 to the third is equal to 729, and if we subtract 1, we get 728. Which is equal to 8 times 91, where y in this case is equal to 91. As we can see, there is a pattern. So far, every value of n has yielded a number which is divisible by 8. So, let's prove this using weak induction. Proof by weak induction that 9 to the nth power minus 1 is divisible by 8 for all n in the set of integers greater than 0. P of n is the following property. A number, 9 to the nth power minus 1, is divisible by 8. Consider the base case, where n is equal to 1. As we have seen, 9 to the first power minus 1 is equal to 8 times 1, which of course is divisible by 8. Now consider the inductive hypothesis for an arbitrary x. If p of x implies p of x plus 1 is also true, and we know that p of 1 is true from the base case, then p of n must be true for all n in the set of integers such that n is greater than 0. Assume that p of n is true, meaning that 9 to the nth power minus 1 is divisible by 8, and therefore 9 to the nth power minus 1 is equal to 8 times y, where y is our arbitrary integer, such that it is also in the set of integers, and it's greater than 0. Therefore, 9 to the nth power is equal to 8 times y plus 1. Now let's consider 9 raised to the nth plus 1 power, minus 1. 9 to the n plus 1 minus 1, using exponent properties, can be rewritten as 9 to the n times 9 to the 1 minus 1. As shown above, 9 to the n is equal to 8 times y plus 1. So, 9 to the n times 9 minus 1 can be rewritten as 8 times y plus 1 times 9 minus 1, which is equal to 9 times 8 times y plus 9 minus 1, using distribution. 9 times 8 times y plus 8 is equal to 8 times 9 times y plus 1. Therefore, 9 to the n plus 1 minus 1 is equal to 8 times 9 times y plus 1, which is of course divisible by 8. Which was ultimately our goal. Since we have shown that p of 1 is true, and that p of x implies p of x plus 1 is also true, then p of n must be true for all n in the set of integers such that n is greater than 0 by induction. End of proof. In this video proof, we accomplished our goal of proving using weak induction that 9 to the nth power minus 1 is divisible by 8 for all integer values of n such that n is greater than 0. We started by convincing ourselves through test cases and intuitive reasoning, and then used our ideas in the inductive hypothesis to write our proof. Thank you for watching, and I hope it was helpful.